Okay, yeah, thank you very much to the organizers for the invitation. Yeah, so I'll talk about the sharp o-minimality and their fatal applications. And I apologize if some parts of this talk might be similar to some of my other talks that some of you might have seen, but some parts are new. So because this is a model theory conference, I try to make some parts more focused on the kind of model theoretic aspects as far as my ability allows. So yeah, there will be also some new content. Okay, so let me start by just like a brief introduction to tame topology, which I'm sure many of you know, but still I want to take to talk about a certain aspect of it. So tame topology, in some sense, it was envisioned by Groth and Dick with his SKISS program, and in his manuscript he had the following quote. He said that after some 10 years, I would now say with hindsight that general topology was developed by analysts and in order to meet the needs of analysis, not for topology. So what he meant was that in general topology you have some kind of strange phenomenon like space filling curves and all kinds of spaces that are not really, it's not phenomenon that we expect to deal with when we are trying to do geometry. And so he wanted to develop some kind of theory that is more tame, where you see really the geometric phenomenon and not some strange noise. And o-minimality was suggested by Van den Dries as a candidate to realize at least certain aspects of this program. And it does meet many of the criteria. So, for example, Groth and Dick was talking about allowing stratifications into smooth strata and triangulations so that you can do homology and cohomology in a natural way. And this indeed is possible in the context of o-minimality. On the other hand, it's quite rich. It contains a lot of interesting sets. So, for example, it contains the moduli space of a billion varieties in some appropriate sense. I will maybe say a little bit more about it later. So it's a result of Kobe and Sergey. And recently, this was also expanded to more general variations of Hod structures by Bakker, Grunewald, Klingler, Zimmermann. And also it has had in the last 10 years or so a deep impact on arithmetic geometry. So this is based on the Wilkie theorem that I will talk about, and then some of its applications in the Diophantine geometry. Okay, so that's the upside. That's why we like o-minimal geometry. But to paraphrase Groth and Dick, o-minimality was developed by real geometers. It was kind of trying to formalize phenomenon that we know from sub-analytic geometry, maybe from sub-exponential geometry. It wasn't really developed with arithmetic geometry in mind. So when we are starting to look at these kinds of applications here to modular spaces and to arithmetic geometry, there's some kind of limit of what we can achieve with o-minimal geometry. And I want to to sell to you some kind of a refinement of the theory of o-minimality that presumably should be more suitable for doing arithmetic geometry. Okay, I'm sorry, just 1 second. I'm in Japan, and my host warned me that the air conditioner might jump back to 28. So let me just adjust it. It's getting hot. Yep, it went up to 28. It's Japanese air conditioners have a mind of their own. Okay, so let me start by describing how tame geometry or o-minimality became connected with the Diophantine geometry. What was this link? And well, it's the Wilkie theorem that I'm sure many of you know, but still I'll introduce it because I want some notation that will be useful for me to present some more general results later. So if X is a set of subset of Rn, I will denote by xgh the set of all points in X that belong to a field of degree G over Q. So they are algebraic, and the extension that they generate over Q has degree at most G, and they have height at most H. So if you're not familiar with this notion of height, then you can just think about rational points. So that's the case, G is equal to 1. And then the height will be just the maximum of all the numerators and denominators of these rational points. And if you consider more general algebraic points, and there is some simple generalization of this, it doesn't matter. Okay, and then what is the Pila-Wilkie theorem? It was already talked about, for example, by Gareth Jones, but I'll repeat. So take any set of real numbers definable in a no-minimal structure. Then the theorem states that the number, roughly states the number of rational points is grows subpolynomially with H. So specifically, we take the number of points in the transcendental part that I'll soon define. We count, let's say, G and H points for G, which is some fixed constant. And then the theorem says this will be big O of H to the epsilon. So smaller than some constant. The constant can depend on the set, on G, on epsilon, times H to the epsilon. Okay, and I didn't tell you what this A tran is. So that's the transcendental part. So first of all, the algebraic part is the union of all the connected semi-algebraic curves contained in the set. And the transcendental part is everything else. And now this kind of result definitely doesn't hold in the semi-algebraic part. If you have an algebraic curve, then when you take G big enough, it has like a lot of algebraic points. So it will definitely fail in the algebraic part, and the theorem says that the algebraic part is the only obstruction. Once you remove the algebraic parts, you get this subpolynomial asymptotic for the number of algebraic points. Now the Pila-Wilkie theorem, originally it was with G is equal to 1, and I guess this formulation is some later result by Pila, but the ideas are roughly the same. Okay, so that's the upshot of this is that o-minimal sets, that even though they are kind of geometrically tame, they actually are somewhat tame also from the point of view of the Diophantine geometry. I mean, there is some like a natural obstruction in the form of algebraic subsets, and once you get rid of this natural obstruction, you don't see many rational points. So that is some kind of arithmetic tameness. Okay, and I'll just quickly mention that because I often get asked this question, so there are analogs of this also for other local fields. So if you work in the p-adic fields, it's a theorem of Clacker, Compton, Lezer, that there's a very nice analog of this. Really, same kind of statement holds for subanalytic sets of QP to the n. There are also analogs for FQT, where Q is big. So in that case, you are counting rational functions over subanalytic sets of this power series over a finite field, and that's due to Clacker's, Lezer, and Fauré. And this was only for Q large enough, depending on the set. And recently, together with Fumihao Kato, we proved this for every Q. So actually now there's also an analog of this theorem for power series over finite fields. And also there is some kind of analog by myself with Novikov and Clackers for CT. So you're counting rational functions in this field of Laurent series. Okay, but I mean, I will focus in this talk on the Archimedean case, just the real numbers. Okay, so the goal is to kind of to push the limits with this Pila-Wilkie theorem. And the first thing to note is that you cannot push these limits in general. So, I mean, that's the asymptotic that we get in Pila-Wilkie. And there are counterexamples that show that you can't do much better than this. For every sequence that is slower than h to the epsilon for any epsilon, you can actually find a set that has at least this many rational points of height h. So you cannot hope to improve the Pila-Wilkie theorem. However, there is a conjecture of Wilkie actually from the original Pila-Wilkie paper, the paper where they proved this theorem, there was also this conjecture. The conjecture was that in some special o-minimal structures, you can do better. So specifically, if you have gamma, which is definable in R sub x, so it's only definable using the arithmetic operations plus the exponential functions, then the number of points in the transcendental part of gamma should be polynomial in the degree and in the log height. So instead of h to the epsilon, we have some power of log h. It's a much sharper asymptotic. And again, the original conjecture, as with the original theorem, it was for g is equal to 1 here. And so I'm kind of generalizing it to also stating that the growth with g is polynomial. This is kind of natural. I mean, in Diophantine geometry, often the role played by log height and the degree is similar. I think that's like a fair generalization of Wilkie's original conjecture. This conjecture is interesting by itself if you want to improve the Pila-Wilkie theorem, but it became more interesting for me and for other people after Harry Schmidt made the following discovery. So what Schmidt noticed is that if this kind of conjecture holds, then you can get Galois orbit lower bounds. I'll give an example of what that means, but you can get Galois orbit lower bounds for abelian varieties, for Shimura varieties, and for other contexts. So in the applications of the Pila-Wilkie theorem in the Diophantine geometry, usually you get some upper bound from the Pila-Wilkie theorem, and you contrast it with a lower bound, what is called the Galois orbit lower bound, which is basically a lower bound on the size of the Galois orbit of a certain kind of point. So like a torsion point in an abelian variety or a special point in a Shimura variety. And usually you get these lower bounds from other fields of math. They come from Diophantine geometry, from transcendence methods. So they were kind of seen as disjoint from this area from the Pila-Wilkie theorem. But Schmidt noticed that if we could prove the Wilkie conjecture, we could actually get Galois orbit lower bounds almost for free. So let me give you a very simple example of how this works in the context that everybody should be familiar with. So it's a context of a root of unity. So that's like the basic case. I mean, the most basic example similar to this case of abelian variety. So an abelian variety is just it's a proper algebraic commutative group, and we are a Galois orbit lower bound there means we want to give a lower bound for the Galois degree of torsion points. So if instead of an abelian variety you take a much simpler group like just C star, the multiplicative group, then a Galois orbit lower bound would mean that I want to know how many Galois conjugate does a root of unity have as a function of its order. Okay, so first of all, that's a well-known and well-understood problem. So we know that all the primitive roots of unity are actually conjugate to each other under the Galois group. So we know exactly how many Galois conjugates you have for a root of unity. But it's actually not very trivial. I mean, in order to know that, you need to know that the cyclotomic polynomials are irreducible. That's why all of the roots are Galois conjugate to each other. And that's not so trivial. There is a proof. It's due to Gauss, but it's not a straightforward proof. And if you try to do the same thing for abelian varieties, then we don't know such a precise description. So what I'm saying is that I'll give you a different proof that works without going through this lemma of Gauss. And that proof actually works for abelian varieties, and it works in the same way for other contexts. So the idea is as follows. Let's look at the graph of e to the 2 pi it going from the unit interval to C star. Now, if we have a root of unity, it gives us kind of a point on the graph, right? Like on this graph, every root of unity corresponds to an algebraic point. When P is a root of unity, then T will be a rational point. And the height of this rational point will be the order of the root of unity. Okay, so if the root of unity had a certain degree G, an order N, then P would give us a Gn point. Okay, it would be a point of degree G, and it would have height n on the graph. In fact, it has height n in this interval, and it has height 0 here, because the height of a root of unity is 0. And not only that, I mean, P gives us this point, but also every power of P from 1 up to n gives us another point, right? All of these powers, they will be defined over the same field. They will be also of degree G, and they also will have order at most n. So they will each give us a point of degree G and height at most n. And then if we apply this something like the Wilkie conjecture, but okay, for a structure that contains the graph of e to the 2 pi t, then we'll see that the number of points, so it's n, all of these powers of n, they are less than the number of points, number of Gn points in gamma. You can have very easily see that in this case, gamma is equal to the transcendental part, because this is just a curve and it's not algebraic. Now this, according to the conjecture, is polynomial in G and log n. So you see that n is less than a polynomial in G and log n. And because log n is much smaller than n, this elementarily implies that n is actually smaller than some polynomial in G. And that is what is called a Galois-orbit lower bound. It tells us that G, the order, should be like some power of n, bigger than some power of n. And you can use exactly the same argument in some other more complicated context. So that is why this conjecture actually became important also for applications in the Diophantine geometry. Okay, so what I would like to do is to, as I said, the Wilkie conjecture is not true in every o-minima structures. There are o-minima structures where you get close to O of h to the epsilon. I would like to introduce some formalism that gives you the kind of, I mean, a sharper kind of o-minima structure where you can expect to prove something like the Wilkie conjecture. And how should we go about this? The idea is that in all of the, I mean, how do you connect tame geometry to arithmetic geometry? In all of these, in the Pila-Wilkie theorem, but also in all of the other proofs of Galois-orbit lower bounds. And I mean, whenever you are kind of mixing some analytic techniques with algebraic techniques, usually what you want to do is you have an analytic set or a definable set in this generality, and you start to let it interact with algebraic sets. Okay, so we are going to find some polynomials that vanish on all of the interesting algebraic points and intersect and do something. So the reason why we cannot get very sharp bounds in general is that we don't really know how definable sets interact with algebraic sets. We only know that, well, if you take, for example, all algebraic sets of a fixed degree, then you have some uniform bounds, depending somehow on the degree. But in order to get good estimates, you need to know more. You need to know how things actually depend on this degree. So you're not working in one fixed definable family, you're letting the degree go to infinity. And then o-minimality just doesn't impose any restrictions on such things. So the idea will be to somehow try to equip the o-minima structure with some notion of degree that and then state how things grow as a function of this degree. Okay, so let me introduce this formalism. So I'll think of an o-minima structure as a collection of definable sets. Okay, just all of the definable sets. So it's subsets of Rn for every n. And on this set, I will introduce a double increasing filtration. Okay, so X will be a union of X, F, and D. So the filtration is parameterized by two parameters. This F is called the format, D is called the degree. And it's increasing in the sense that if you increase the format or you increase the degree, then you get a bigger collection. And you should think of the format as, so if we were in the semi-algebraic context, for example, the format would be something like the ambient dimension. And the degree would be something like the degree of the semi-algebraic set. So say the sum of the degrees of all the polynomials used to define the semi-algebraic set. But you don't, I mean, in general, it's just an axiomatic thing. So I'm defining such a filtration, and now I will list some axioms that this filtration should satisfy. So I'll say that X is sharply o-minimal if First of all, for any case sets, AJ, I want the union of the sets and the intersection of the sets to have format f plus 1, where f is the maximum of all of the formats of these sets, and degree d, where d is the sum of the degrees. Okay, sometimes I mean, there are many slightly different definitions that are equivalent, like you can say that the union has format f instead of f plus 1, but it's not very important, so I decided to give this some simpler form here. So, okay, I want this closure property under unions and intersections. And similarly, I want that if you take one of the sets and take a complement, or you take some projection, then the format is increased by 1 and the degree is fixed. Okay, so these axioms, they're not really about o-minimal structures. They're about just first order structures. I mean, you could make this definition for any first order structure, and it would make sense. Maybe it would be interesting. Okay, but I mean, to talk about o-minimal structures, I want to say something about interaction with the real field. Okay, so what's an o-minimal? I'm always thinking about o-minimal structures over the real field. So I want to say that the filtration is interacting reasonably with the usual filtration that we have in mind on the real field. So the way that I state this is by saying that if you take an algebraic hypersurface in Rn, this will have format n and degree equal to the degree of the hypersurface. Okay, so on the algebraic hypersurfaces, the filtration is kind of compatible with the usual filtration. So this is already axiom. This is kind of the axioms of a structure of the real field, but it's still not about o-minimal structure. So an o-minimal structure, it is built up of these axioms plus one more axiom saying that if you have a definable subset of R, it will have finitely many components. And the way that I make this sharper in this context is by requiring that the number of connected components of a definable subset of R should be some polynomial in the degree depending on the format. Okay, so for every value of f, there is some polynomial depending on this f, and the number of connected components is this polynomial evaluated on the degree. So it says that the number of connected components grows polynomially with the degree for each fixed format. So this is exactly the kind of thing that we should know if we are hoping to do some sharper kind of things in arithmetic geometry, like proving the Wilkie conjecture and getting a lower bound, that kind. Okay, so the first question is it a reasonable notion to consider? I mean, okay, I gave a list of axioms, but they look quite strong, and it's not clear if there are any examples. Okay, the semi-algebraic sets are an example. It follows from classical result that semi-algebraic sets are an example. But beyond the semi-algebraic sets, do you have any examples? That's the first question. So this is kind of motivated by, it's not coming out of the air, it's motivated by the Pfaffian functions. It's one of the origins of o-minimality. You know, it was used to establish the o-minimality of R sub x. And this theory of Pfaffian functions actually has this kind of flavor. So when you're working with Pfaffian functions, I mean, Gareth gave some more details in his talk, but basically the Pfaffian functions are defined by some system of equations involving a certain tuple of functions. So all of this you can think as part of the format. And a Pfaffian function also has a degree. And Chovansky's main theorem is that if you consider a system of equations of a given degrees, then the number of solutions will grow polynomially with the degree. Okay, so it's exactly the kind of thing that we would want if we are trying to build this kind of sharp structure. But Chovansky's theorem was only for systems of equations. It wasn't about logical structure. So to get a structure, you need to close on, you need to add the order relation, you need to close under complements, under projections, and then you would get a structure. And this is something that was considered in many papers by Gabrielov and Vorobyov mostly, and some other people. And they proved various results both in the restricted and unrestricted setting. So restricted means you are taking a Pfaffian function and restricting it to some like a finite domain, such that everything, I mean, it's Pfaffian and continuous all the way to the boundary, including the boundary. And unrestricted is something like you take the exponential function on all of R. So you like all the way to the singularity at infinity. And I mean, it matters in these questions, whether you're doing restricted or unrestricted, and Gabrielov and Vorobyov got various results in each of these contexts. And they actually almost got a sharply or minimal filtration. I mean, a filtration that satisfies all of these axioms. There was only one problem, which was that for the complement, they could only prove, I mean, they proved some effective result. They showed that if you have A of a given format and degree, then the complement has some format and degree as well. But the format was depending on D for them. So you see, I required here that the complement has a format F plus 1. It's not so important if you put here F plus 1 or 2F or some function of F. But what is important is that it shouldn't become dependent on the degree, because we are trying to always keep everything polynomial in the degrees. We are not asserting how things depend on the format. So if you do something and your degree leaks into your format, and then in the next step you do another thing, then now it depends in some bad way on the format, then it will depend in some bad way on the original degree. So you have to, like, the main thing is you have to keep the degrees kind of by themselves, not let them go into the format. So this one letter ruins everything. The fact that your format depends on the degree, it makes all the rest kind of stops working. And it wasn't some oversight. I mean, we really don't know how to prove that the AC has a format not depending on D, at least not with their filtration. So, I mean, it's a real problem that we still have. And a closely related question is cell decomposition. So suppose that you have a sharply or minima structure, or you have this, structure of restricted Pfaffian functions or something like that, and you have some definable sets. Can you make a cell decomposition with good control? So do you know that the number of, when you do a cell decomposition, the number of cells will grow polynomially in the degree, the number of sets, and the format of each cell will be just a constant depending on the formats, but not on the degrees of the previous cells. And we also don't know the answer to this. I mean, even if we can build a sharply or minima structure, we don't know that you can do cell decomposition. And for me, this would make the whole thing kind of pointless, because o-minimality is kind of defined in order to get cell decomposition. Every proof in o-minimality that I know of almost uses cell decomposition. So if you can't get cell decomposition, you might as well choose different axioms. So that is an argument for why this theory of sharply or minima structures is not such a good theory. If you can do cell decomposition, maybe somebody can prove that cell decomposition is possible with these axioms. I don't even have a conjecture. However, there is a way of rescuing this, and this is based on a theorem of Vorobyov and myself. So what we proved is that even though this filtration that Gabrielov and Vorobyov introduced we can't show that it's sharply or minimal, we can find another filtration, omega star, that contains omega. So I mean, it's bigger. All the sets that had format F and degree D with the original filtration, they still have format F and degree D with the new filtration. But this new filtration is sharply or minimal, and it also has this sharp cell decomposition. Okay, so it means that the restricted Pfaffian structure is sharply or minimal, just not with the original filtration that Gabrielov and Vorobyov were using. So I'll say roughly that this new filtration is basically, we take the old filtration of Gabrielov and Vorobyov, and then we take the sets there, we take their connected components and their projections, and all of these sets will be defined to have format F and degree D with this new filtration. And it turns out that when you do this, you get actually a filtration that satisfies these these axioms that I listed before. And together with Novikov and Benny Zack, we actually repeated this argument for a general sharply o-minimal structure. So we show that if you have a sharply o-minimal structure, then there is another filtration, a bigger filtration, omega star, defined in roughly the same way, such that with this new filtration, your structure is still sharply o-minimal, but it does have sharp cell decomposition. Okay, so basically, you are always allowed to assume without loss of generality that your structure does have sharp cell decomposition. If it doesn't, then you just choose a new filtration and it will still be sharply o-minimal, and now it will have sharp cell decomposition. And as I said, the proof of this theorem is very similar to the proof of this theorem. It's kind of, we're just formalizing it in this language of sharp o-minimality. So let me show just one example of a corollary that you can get with this. So suppose that you have X of format f in degree D in a sharply o-minimal structure. Then X has a triangulation with poly FD simplices. So the number of simplices in the triangulation is some polynomial, depending on the format, in the degree. And the proof goes like this. First of all, we can assume that we have sharp cell decomposition. We can, if we don't have, we'll replace it by a new filtration where we do have sharp cell decomposition. And then you can just follow the triangulation proof from Lau's book on o-minimal geometry. And basically, because it's a proof in o-minimality, all that you can do is use these axioms. You are using these operations in the proof, and you are making maybe cell decomposition. And you can just follow it step by step and see that you always get polynomial control in the degree. So not just this proof, but many proofs, most proofs that you do in o-minimal geometry, if you have these axioms and you have sharp cell decomposition, then you can repeat them and get good polynomial control of the kind of a complexity of what you get. Just I'll try to adjust the air conditioner again. It's getting hot in here. 1 second, sorry. Yeah, it's all written in kanji. I don't know if maybe I'm turning it on heat or something. Anyway, so yeah, so now let me talk a little bit about point counting, like Wilkie and those kinds of theorems. So there's a theorem that Gareth mentioned. Well, he stated it for the restricted Pfaffian case, but actually the same proof works with these axioms for a general sharply o-minimal structure. So the theorem says that if you have a definable set of format f in degree D and epsilon greater than 0, then the number of points in transcendental part is some polynomial in D. The polynomial depends on the format, the degree of the point, and epsilon, times h to the epsilon. So basically, the asymptotic constant of the Wilkie theorem can be shown to be some explicit quantity that depends polynomially on the degree of the set. And this is quite useful in applications. When you have a sharply o-minimal structure, it's useful in the applications to the Diophantine geometry. So Gareth mentioned some applications to Manin-Mumford for products of elliptic curves, and there are other kinds of applications of this. And this is basically the best that you can do, I think, or the best that I know of for a general sharply o-minimal structure. But the goal of introducing this sharp o-minimality was also to improve the asymptotic to something like the Wilkie conjecture. So for that, I need one more technical condition. So I'll say that the sharply o-minimal structure has sharp derivatives if, whenever we have a function, when I write this, I mean, say that the graph of the function is a definable set of format f in degree D, and I consider some derivatives. So this is multi-index notation. I'm considering some, like a mixed derivative, higher order derivative. Then this will have a format that is it's some constant depending on the original format, and the degree which depends polynomially on the degree of the original function and the order of the derivative. So kind of the important thing to notice here is that the format does not depend on the order of the derivative. Okay, so this is what you expect when you are dealing with functions that satisfy differential equations, say algebraic differential equations. When you have a function satisfying, like a Pfaffian function, satisfying algebraic differential equations, if you take a higher order derivatives, you can express these derivatives as polynomials in the original functions. Okay, so when you compute higher order derivatives, you will just get some polynomials of some larger degree, but it will be polynomials in the same number of variables. That is why the format doesn't grow, only the degree grows, and the degree grows polynomially with the order of derivative that you took. Now, we don't know how to prove this in general. In general, F alpha is definable always. Whenever you have a sharply o-minimal structure, you can show that F alpha is definable. Just write a formula for it. But the number of quantifiers that you have in this formula will depend on the order of derivative. So if you try to prove it like that, you will get that the format depends on alpha. Okay, so that is why this is some extra condition as far as I know. I don't know how to prove that every sharply o-minimal structure has this property. But as I said, for example, the restricted Pfaffian structure, it does have this property, exactly because all your functions are basically defined in terms of some differential equations. And then the recent theorem that I proved with Novikov and Zack is that if you have a sharply o-minimal structures with sharp derivatives, then you get this polylog count. So the number of GH points is some polynomial depending only on the format of the set. And it grows polynomially with the degree of the set, with the degree of the points, and with the log height. Okay, so this is the kind of thing that some strengthening of the Wilkie conjecture, with a small caveat that we don't know yet that Rx is sharply o-minimal. Okay, so this is, we get this nice result, for example, for the restricted Pfaffian structure, but not for Rx. However, as a corollary, we do get Wilkie's conjecture for Rx. This is based on a certain argument that Gareth also mentioned. So basically, it's using Wilkie's theorem of the complement. So we say that every set that definable here is just a projection of some definable set in Rx, of some quantifier-free set. And then you can restrict this quantifier-free set to some very large box. And because you get uniform bounds, then you actually count all of the interesting points in your set. But okay, I don't want to go into details, but I just wanted to mention that we do get it for Rx. It's the original conjecture, but it's in a kind of more roundabout way. However, I want to mention some kind of ongoing work, which has maybe a bit of familiar model theoretic taste. So suppose that you want to go beyond the restricted case. So I'll think about two structures. S tilde is just any o-minimal structure, some big structure. And inside it, I have S, which is a sharply o-minimal structure with some filtration. So for example, you can think about the Pfaffian structure, this S hat. And inside it, you have the restricted Pfaffian structure generated only by restricted Pfaffian functions. So that's a smaller structure. Now, suppose that you have a family which is definable in S hat. I'm thinking about it as a family of definable sets parameterized by this epsilon parameter living here. I'll call it omega finite if, well, basically the format and the degree of the fiber is uniformly fixed. So there is some f and d such that for every epsilon, this fiber x epsilon lives in omega fd. So the whole family doesn't need to be in S at all. But I'm saying that every fiber separately is in S. So for instance, you can think that I have an unrestricted Pfaffian function, like the graph of e to the x. And then a family will be just the restriction of this unrestricted thing to bigger and bigger boxes. So as epsilon goes to 0, I'm kind of going to see the whole graph, but for each fixed epsilon, non-zero, I mean, in the open interval, it will be a restricted function. And the limit of this fiber, so I take a topological closure and then take the fiber over 0, this will be an omega limit set. Okay, so for example, in this process, an unrestricted Pfaffian function, you can see it as a limit of restricted Pfaffian functions. And then the theorem that we are currently in the process of writing with Gabrielov and Vorobyov is that the structure generated by the limit sets is sharply o-minimal. Okay, so if you start with this setup, you can take the limit sets, which a priori can be bigger than S. It might be all of S hat. And we do know how to put a sharply o-minimal filtration on the structure of limit sets. It's based on some older papers of Gabrielov and combining with my recent paper with Vorobyov. So for example, if you are looking at the Pfaffian context, if you look at there is the restricted Pfaffian inside the Pfaffian structure, and the limit of the restricted Pfaffian structure is just the whole Pfaffian structure. Okay, because every Pfaffian function is like a limit of its restrictions to bigger and bigger boxes. So in this way, we expect to get that the Pfaffian structure is sharply o-minimal, and that should mean that this Wilkie's conjecture in Rx will follow in kind of a more direct way, and we'll get this good dependence on all the parameters. Okay, so now I want to get to the main conjecture, what I consider the main open problem here. So first of all, I defined some like a sharply o-minimal structures, and you can ask, is it even more restrictive than the usual structures? The answer is it is more restrictive. So for instance, R sub n, the structure of globally subanalytic sets, is not sharply o-minimal. And the reason is that you can find some analytic set gamma. For example, it could be the graph of some lacunary power series. And this analytic set can intersect a polynomial equation P is equal to 0 in more than a polynomial number of points. I mean, I can set it up so that the number of intersections with some polynomial of degree P is like 2 to the power D. Right? So it will not be smaller than any polynomial in the degree. And that's why no matter what kind of filtration you put, gamma will have to have some fixed format with respect to this filtration, and you just cannot have the right kind of estimates. So I would say that this kind of gamma is, okay, it's tame for o-minimality, it lives in R sub n, but it's not tame for Diophantine geometry. That's exactly the type of gamma where you get too many rational points. You get like h to the epsilon instead of log h rational points. So I mean, we are excluding these kinds of lacunary power series sets that interact in a strange way with the algebraic structure. Okay, so some structures aren't sharply o-minimal, and the question is, what is sharply o-minimal? And the conjecture is that all the functions coming from geometry, whatever that means, live in a sharply o-minimal structure. So coming from geometry, I put it in this scare quotes. You can I mean, interpret this in various ways. So I'm thinking, for example, about all the covering maps of all Shimura varieties, all the period integrals. I mean, these kinds of functions that come up naturally in in Hodge theory, in algebraic geometry. You could also ask, about the gamma function. There was a talk of Patrick dealing with the, can you put the gamma function? Can you put the zeta function in o-minimal structure? So I would think that these functions also should live in a sharply o-minimal structure, but I have no idea. Okay, but one important example for many of the applications is the uniformizing map of the abelian scheme of, the universal abelian scheme over the moduli space of abelian varieties. So that basically means you're looking at all abelian varieties of a given genus at once. They each have a uniformizing map, like from C to the G, there's a map to these abelian varieties, and you consider the whole family of those, and you consider the universal covering map. And this is actually definable in RNX. That's a result of Kobe and Sergey. They did it by showing that some theta functions are definable. And in terms of these theta functions, you can realize this, this universal covering map. And this is a very important result in these applications in Diophantine geometry. So when you prove the under-odd conjecture for for AG. For example, you use exactly these kinds of maps. Okay, so, for example, I would very much like to know if this result of Peterzil and Starchenko holds in the sharp sense. So is there some sharply o-minimal structure that contains these guys? We don't know. I don't know. So I mentioned partial results. So there's a result of Yakovenko, Novikov, and myself, where we proved some uniform bounds for period integrals of one-dimensional families. So, I mean, these period integrals are the kind of things that you get when you try to explicitly realize these functions, these universal covers, but we could do it only for one dimension. So it was like systems of equations of one variable, one equation in one variable, and we didn't get polynomial growth. So it's uniform, it's somehow in the direction of o-minimality, but it's not good enough. And there's another more recent result where I got some, this time polynomial bounds. So I got bounds that grow polynomial in the degrees like we want. And it's also for systems of equations involving leaves of some more general algebraic foliations. But there, the result is not uniform. So it doesn't depend only on the degree and the format. It depends on things like the log heights of the coefficients and the distance to some degeneracy locus. So it's also not good enough to hope to get this sharp o-minimality. And presumably, if you can combine the advantages of both of these, you would be close to sharp o-minimality, but I don't know if it can be done. And currently, it seems very difficult. So I expect that this conjecture is still quite difficult. Okay, let me talk about a little baby case of this result of Peterzil and Starchenko. So suppose we want to uniformize just a fixed elliptic curve or a fixed abelian variety. So not this universal family, but just a fixed one. So I'll start with the case of elliptic curves. So you have an elliptic curve, E, it's a quotient of C. And suppose that I want to choose a simply connected subset. So I'll denote by this E circ. It will be E minus some standard branch cut. So I'm going to make some like semi-algebraic branch cut in some simple way, like, cut off the real line and some circle. Doesn't matter exactly how you make this branch cut, but it should be algebraic. And then you can consider this map kind of going back from E to C, right? I mean, okay, of course, there's no map going back from E to C in general, but after you make a branch cut, you can leave this map. So this map will be just the integral of the holomorphic form, and it will be a well-defined map landing in C. Okay, but it's only defined minus some branch cuts. And now there's a very nice result of Jones and Schmidt that says that the image of this map meets some fixed number of fundamental domains n, where n is an effective constant that doesn't depend on anything. It's a horrible constant, but it doesn't depend on which elliptic curve you chose. So the elliptic curves, the family of elliptic curves, it's not compact. They can degenerate. So presumably, you might get here something depending on the elliptic curve that you chose. But the result says that it actually doesn't depend on which elliptic curve you chose. And because you meet some fixed number of fundamental domains, then it kind of says that this you can translate as saying that the map going back from C to E is definable. I mean, to define the map from E to C or from C to E is kind of the same thing, minimal geometry, but you want to define the graph of the map on some fundamental domain, the standard fundamental domain. So if somehow you go through too many fundamental domains, then you will need to build up your map out of many, many pieces. As soon as you meet only finitely many fundamental domains, you're clear. You get the definability result. And this is actually the result that we use in many applications of this effective Pillow-Wilkie theorem, to prove Manin-Mumford conjecture effectively and these kinds of things. So I want to describe some in-progress results where we extend this from elliptic curves to general compact Riemann surfaces. So suppose now that you have a compact Riemann surface of genus G, and you make some again, you make some branch cuts, so you have a simply connected domain, and then you can again define a function. This time, it will not go to C, it will go to C to the power G. So it will be the integral, you can integrate some G holomorphic forms. You have a Riemann surface of genus G, there are G linearly independent holomorphic forms, and you can integrate them. And that gives what is called the Abel-Jacobi map. And again, in CG, there is some lattice of periods, and you can look at the fundamental domain, and you can ask how many fundamental domain does the image of this map meet. And our result that we are in the process of writing is that it again meets n fundamental domains, some universal number, not depending on the curve. And moreover, n is polynomial in G. So this part we are still kind of writing, so you can take with a small grain of salt, but I hope that it's in fact polynomial in G. And the upshot of this, I mean, one of the implications of this should be that we get an effective, like Peterzil Starchenko result, where now you can repeat this construction that I did here for all of the curves at once. So you can look at this abelian scheme of genus G consisting of all of the abelian varieties at once, and look how many fundamental domains they meet in this big covering space. And again, it will be an effective constant. There are many steps to go from this to this, because this is only about compact Riemann surfaces, and this is about general abelian varieties. So there's some extra work, but I mean, this is kind of the direction, and the hope is to get some kind of more effective version of this Peterzil Starchenko result. Okay, so to finish, I want to say a little bit about some applications of this stuff in the Diophantine geometry. So the first one is for Andre Oort. So it's a theorem about you have a Shimura variety, you have V, which is a subvariety of the Shimura variety, and then the theorem, which used to be a conjecture, is as follows. I'll give a kind of a simplified statement to make it easier to present. So suppose V doesn't contain positive dimensional special subvarieties. So there are some special subvarieties that form an obstruction, but suppose we don't have this natural obstruction, then V contains finitely many special points. And so many people have contributed to the proof of this theorem in this generality. The original, I mean, the case of modular curves, which was the original conjecture, is due to Jonathan Pila. And the most general case I'll mention in the next slide. Okay, so I mean, suppose we knew that the universal cover of a Shimura variety is definable in an o-minimal structure. That's kind of part of my this big conjecture that I said. It should imply this in particular. And then we would get that the finite set of special points can be computed in polynomial time. So if you are given a system of equations for V, encoded in bits somehow in the computer, then there's a polynomial time algorithm that computes all of the special points. And the idea basically is that the proof, if you follow the proof of Andre Oort, it is kind of I mean, you can get some upper bounds for the special points. You can get the potential list of special points, assuming that you can make the counting effective. And if the counting is really depending polynomially on the degrees and everything as implied by the conjecture, then it will be a polynomial time. And well, I mean, this is a consequence of this conjecture, but actually it follows already from my partial results on foliations. So even though this result on foliation doesn't prove sharp o-minimality, if you just look what is needed in order to apply it in this context, it does prove what is needed. So this result of foliations, kind of almost in each particular case, it is general enough, but somehow it's not general enough to do the general theory. Okay, I will make a small caveat though that this is kind of an existence result. So I'm saying that there is a polynomial time algorithm, but I'm not saying that we have an algorithm, that we know what the algorithm is, because this algorithm depends on some constant, the Siegel constant appearing in the Galois-Lorer bound. And this is a constant that we know exists, but we don't know what it is. So the algorithm should start with the first line saying the constant is equal to something. That would be the first line of the algorithm. And once you have that, then we have an algorithm. We don't know what the constant. Okay, so this is a kind of an application of Pila-Wilkie type counting, and there are many other applications of this kind for for results about the torsion points in billion families, and work of Maserzani and many other people. Can be many of the cases where you have applications of Pila-Wilkie. If you have sharp o-minimality, then you can actually get this kind of effective computation theorem. And in fact, in most cases, you can get it already from this partial result on foliations. Okay, but finally, I want to mention one other result, which is kind of it's not a Pila-Wilkie, it's really an application of the Wilkie conjecture. So for that, I'll go back to the Galois lower bounds that I mentioned earlier in the talk. So now in the context of Shimura varieties. So suppose that you have a special point in Shimura varieties. What is a Galois lower bound that we want? We want to know that if you consider the Galois conjugates of this point, then their number will be bigger than some constant, depending on the Shimura variety, times a power of the discriminant. So the discriminant, so usually, let's say if you're in AG, so your special points are actually abelian varieties, then the special ones are abelian varieties with complex multiplication. It means they have many endomorphisms. And then they have kind of as many endomorphisms as possible. And then the discriminant of this ring of endomorphisms is the discriminant. But if you don't know what it is, then doesn't really matter. I mean, it's some parameter that measures the complexity of the special point in the same way that for a root of unity, we measure the order of the root of unity. Okay, so for a special point in Shimura variety, we measure this discriminant. And what we want is this kind of lower bound, and Zimmermann proved this lower bound for AG. So for the moduli space of principally polarized abelian varieties of genus G. And he got this as a consequence of two facts. One is a height bound. So we want to know that the log height of a point is less than the discriminant to the epsilon. Okay, so this follows from average Kolmez, a very deep recent result. And the other ingredient in the proof was the Maser-Wustholz isogeny estimates. And the problem was that neither of these things are actually known to hold if you go to general Shimura varieties. That is why Zimmermann proved it for AG and not like the full conjecture for all Shimura varieties. And the idea of Harry Schmidt, when he thought about this approach for Galois orbit lower bounds, it was basically in order to try to prove this in general. That was the key motivation. And together with Schmidt and with Andrea 5, we actually carried out this program. So we showed that if you have a height bound, then you get a Galois bound. You don't need the Maser-Wustholz isogeny estimates. And it was basically based on this original idea of Harry, that you count the points on the graph of the universal cover, and this kind of counting argument gives you a lower bound for the degree. And this is, again, based this time on polylog counting. You can't do it with Pila-Wilkie type counting. And so it would follow immediately from this conjecture on a big sharply o-minima structure, but actually we did it using my foliations result. So again, for the specific set that comes up here, the graph of universal covering map of a Shimura variety, you can get it from my foliations counting result. And then a few months later, Pila, Shankar, and Zimmermann, also, I forgot to say, but with a very important appendix by Helene Henault and Michael Groschenig, they proved that this height bound, the first one, actually also holds for general Shimura varieties. So they reduced the height bound to the height bound in the case of AG, which was already known. So this is another very deep result. But combining this with this implication, it means that we do have a Galois bound now for every Shimura variety. And it was already known, based on the strategy of Pila and the work of many people, that this gives, this was the last ingredient that was needed to prove under oath. We needed the Galois orbit lower bound. So actually with this theorem, Pila, Shankar, and Zimmermann proved the general case. And the proof of the general case now really relies on polylog counting. We don't know another way to get the Galois orbit lower bound without polylog counting. So again, here, in this case, and also in the previous cases where we proved the specific thing that we needed for this polylog counting argument, we used my foliations argument, but it is a little bit ad hoc. You have to analyze each situation separately. If this theorem, if this theory of sharp o-minimality matures, then this implication should become very easy. So, I mean, that is the kind of what we can hope to gain by proving this kind of this very difficult conjecture. Okay, I see I'm out of time, so I'll finish here. Thank you very much.